The next application we're going to do is growth and decay problems. So here's the general formula. C is going to be the initial amount. The base is going to be fixed at E. The K up here is going to be nice when you write it in the base in this format because you can actually see whether you've got a growth rate or decay rate. If K is positive, it's a growth rate. If K is negative, it's a decay rate. And then T is the quantity of time. You can also write it as F of T. Same concept. So let's do some examples. This one's from your textbook. We've got a culture of bacteria originally numbered 500. So right away, I know that C is going to be 500. So I have Y equal to 500 e to the kt, because 500 is my initial value. After 4 hours, there was 8,000 bacteria in the culture. So my T, in this case, is going to be hours. And I know the ordered pair 4, 8,000 is my output. I can now use this to find K. So I'm going to plug these values in. When Y is 8,000, I don't know K, but I know T is 4. So what you're going to do here is you're going to isolate the E all by itself. So you're going to divide by 500 on both sides. So that's going to leave you with, I'm going to get lazy here, when I take the 8,000, I'm going to divide it by 500. I get 16. So I have 16 equal to e to the 4k. Now there's a shortcut that you can do here, and your book isn't going to show this to you yet, but I'm going to go ahead and show it to you. E's and ln's are inverse functions, so I'm going to put both of these inside of an ln. And the beauty of doing that is that the e and the ln cancel, and then you're left with the ln of 16, which is just some number, equal to 4k. So now that I have 4k equal to the ln of 16, to solve for k, I'm going to divide both sides by 4. So that gives me k is equal to the ln of 16 over 4. And you can do a decimal approximation for that if you want to. Here's the ln of 16. I'm going to divide that by 4. Not 44. And I get 0.69315. We'll try to give as many decimals as we can for that. So that brings us back to, now my equation is going to be 500 e to the 0.69315 t. And if you want to know the growth rate, it's 69.3%. So this bacteria is growing very fast. It says if we assume bacterial growth, how many bacteria will there be after 10 hours? So what you're going to do here is you're going to let t equal to 10, and you're going to plug it into that equation. So you have 500 e to the 0.69315 times 10, and that'll give you the approximation of the bacteria. So I'm going to have 500 e to the 0.69315 times 10. So in about 10 hours, you have about 512,014. Don't give me part of a bacteria there. So that's one example that we have of an exponential growth problem.